Hi there, this is Alex with Knowm Inc. and this video will give you an introduction to the classify experiment on the Memristor Discovery platform. Okay, so first things first, we go to the help menu and you're going to want to make your way through all of this material. It will give you an explanation of a lot of what I'm about to show you. Most importantly, you're going to need the version 1 board and the 21x8 AHA node adapter board. You can get this on the web store. The purpose of this board is to allow us to form 8 2-1 synapses, or 1 2-1x8 AHA node, from 2 discrete MIM inline memristor chips. And so a 2-1 AHA node is in reference to the synapse configuration. So 2 meaning the number of inputs, 2 inputs, 1 output. So it's a differential pair in which you're driving the top and the bottom, and then the voltage divider at the middle constitutes your output. So 2, 1. This adapter board allows you to plug in 2, 4, or 6 chips. This affects the redundancy of the AHA node. So as you add more chips, you're not adding more synapses so that you can execute, say, bigger spike patterns. You're adding redundancy to the underlying synapses themselves. So if you add 4 chips, you're going to have 2x redundancy. So every time synapse 1 here is active, you'll end up actually activating 2 synapses at the hardware level. Redundancy is important in AHA computing. It allows you to achieve more deterministic and reliable operation when some of your memristors aren't working for whatever reason. Maybe they're stuck, maybe they have a very high variance in adaptation rates. Lots of different reasons in the real world why your underlying hardware isn't working as perfectly as it should. We don't live in an idealized world. The whole reason why most of our electronics is digital is to make up for the fact that there is unreliability and noise and various other things. So redundancy is an important thing to understand and to exploit. Maybe you have some old chips lying around, maybe you burned out some of the devices. It doesn't mean you can't use them. You can just make up quantity for quality. So more synapses allows you to average out all the adaptation rates, various other things. Okay, so you have the adapter board and you have the version 1 Memristor Discovery board. So let's move this out. Let me give you a tour of the experiment itself. We have these 2 plots here, which I'll be going through once we get going. On the control panel, we can select the type of pulse that we're going to be using to execute our instructions on the AHA nodes. This is a reference to the KTRAM instruction set. We're just going to leave that here default with a square smooth pulse type. We can change the voltage amplitude of the pulses. You're going to want to play around with this until you find a nice place that will affect your memristors. And you can change the pulse width. You can also play with this. If you've never used the devices before, or you're operating in sort of higher resistance states and the RC effects of the board become a problem, then you're going to want to increase the pulse width to try to mitigate that. We have just a few things that we can configure. The AHA routine is in reference to the particular sequence of KTRAM instruction sets, the programmatic instructions that are used to implement the classification learning algorithm. These are fairly simple, but you can use the KTRAM instruction set to implement all sorts of different machine learning algorithms, and this one is about classification, and there's more than one way to make a classifier. The data set is the patterns that we're attempting to learn. This is a 8 synapse AHA node, so we don't have too many synapses to play with. So our patterns are fairly simple, but they proceed from easy to difficult, and I will go through that in just a second. Training epochs is how many times through our data set are we going to be learning. So we're going to take this AHA routine, we're going to take the data set, and we're going to execute this many epochs of training, and we'll plot the results here over time. Okay, going back to our help menu. We can look at the AHA routine. We've shown 3 different AHA routines for classification learning. There's more than that. I highly recommend, if you've gotten this far, to get your hands on the source code of Memristor Discovery. Go in there and start fiddling around with this. Make your own routines. Add your own data sets. So the three different types is learn on mistakes. This is essentially exactly what it sounds like. At first, it loads the spike pattern, and it executes a low voltage read operation, and it extracts the state of the node, which is Vy, the voltage on the Y node. And if that voltage is less than 0, then the node is said to be negative or false. And if your supervised pattern state is true, then it's made a mistake. So it needs to increment all the synapses high so that it won't make that mistake next time. Vice versa, if it outputs a positive state, but the supervised label is negative, then it needs to decrement all the synapses. And again, it only makes changes via the RH or RL instruction if a mistake has been made. The learn always routine is exactly what it sounds like. It doesn't care if it makes a mistake or not. It just takes the supervised pattern label and it executes the corresponding instruction. So if the supervised label is true, then it's going to increment the value of all the synapses positive, and if the supervised label is false, then it'll decrement all the synapses negative. The learn combo is a combination of learning on mistakes and always learning. This is actually useful in some instances that I won't go into. In this case, if the supervised label is true, then it will always increment the memristors or the synapses high. On the other hand, it will only decrement the synapses low if it's made a mistake by outputting positive when it should have been negative. The data sets proceed from simple to hard. Now, because we're dealing with hardware here, what might be a very simple software problem could actually be more difficult with hardware if your underlying hardware is unreliable. Let's say one of your synapses doesn't work. Well, if one of your synapses doesn't work and classification of a pattern requires that that synapse work, then you're not going to be able to learn it. It's actually fairly difficult. And the way that you make up for that is by adding redundancy. Okay, so I showed you how to add hardware level redundancy with the adapter board by plugging in more chips, but you can also have software defined or pattern level redundancy. So the ortho 2 pattern is an example of this. We're learning a very simple 2 patterns. One is true, one is false, and because we have 8 synapses, we can allocate 4 synapses per pattern. Okay, so we have a 4x pattern level redundancy here. So if 1 or 2 or even 3 of the synapses underneath one of those patterns doesn't work, it can be made up for by a function in 4th synapse. Okay, orthogonal is in reference to the fact that the synapses do not overlap. So the pattern that constitutes true, synapse 0, 1, 2, and 3, does not overlap with the pattern that is false, which is synapse 4, 5, 6, and 7. Anti-ortho 2 pattern is exactly the same, except the labels are flipped. So if you've just learned the ortho 2 pattern and you want to unlearn it and flip everything over and make sure all your synapses are functioning and working, you can pick the anti-pattern, anti-data set, and you'll know that everything has to flip and change in order for the thing to learn. So ortho 4 pattern, just like the 2 pattern, except now we have 4 different patterns. Because we have 4 patterns, 8 synapses, we can allocate 2 synapses per pattern. This gives you 2x pattern-defined redundancy. The anti-ortho 4 pattern is exactly the same thing, only the labels are flipped. The ortho 8 pattern has no pattern level redundancy. Every synapse, each activation of each individual synapse is its own pattern, and you're going to have to drive each synapse to a positive or negative state in order to learn that. So if you do not have any hardware level redundancy and all your memristors working in all your synapses, then you'll be able to do the ortho 8 pattern or anti-ortho 8 pattern. However, it could be quite difficult or impossible if some of your memristors don't work. Proceeding on, we get to the 2 pattern 2-5 frustrated. So what this means, it's 2 patterns, but each pattern is composed of 5 spikes, but 2 out of the 5 spikes or active synapses are active for both the true and the false label. Okay, so that means that, let's say it's trying to learn the true label, and so it's incrementing the synapse as positive, then it's trying to learn the false label after that, and those same 2 synapses are active now, and it's trying to decrement them. Okay, so it's moving them up, it's moving them down. Those synapses being active isn't really useful for learning the classification problem, and it's trying to flip them up and down, and really the classification algorithm has to learn to ignore them. It's distraction. So frustrated synapses need to be tuned to 0 ideally with your classification algorithm. And the 2 pattern 2, 3, 4, 5 frustrated is exactly the same thing. It just adds 2 more frustrated synapses. Okay, so we've gone through the introduction, showing you the controls and the Halt routines and the data set. Now let's actually do some classification. We are now going to attempt to learn a data set with a Halt routine. And to do that, let's just start with some of the defaults. So let's say learn on mistakes. Let's just pick the, let's say, ortho 4 pattern, and let's keep the amplitude and voltages at their default settings, training epoch at the default settings, and click learn. Okay, so on the top plot here we show the accuracy over time. It started at 0 and it's moving up. Now it's at 50-50, so it's really not doing very well. You can see that there's one synapse which is positive and all the other ones are negative, and they're really not budging. Now I'd like to explain to you what's going on here. So if you see this, you'll know how to fix it. Okay, so this is actually indicative of RC problems. Recall that if the memristors of your synapses are in very high resistance states, then it takes time for the charge to bleed off that VY node. And that can cause this inversion, which will sort of wreak havoc with your instructions. And this is actually manifest if your synapses are all mostly negative, then this is a clue that this is what's going on. Now to show you this, let's go to the Synapse app. Let's just take a look at the help menu here. So what we can see, this is what you're going to want to read. It's about this sort of synapse initialization. So here you have your synapse, M1 and M2. Now in our AHA node, it's really just a bunch of these things in parallel, and we've just sort of selected some subset of them, and we're activating them all together. Now what happens is that if the resistance of M1 and M2 is high, then the capacitance on node VY here will cause there to be accumulation of charge, that when the pulse falls after the instruction, it takes a while for that charge to bleed off. Whereby the voltage is flipped, say on the VA node here, and you get this polarity inversion. And you can see that here, it's sort of highlighted in red. Okay, so the blue trace here on the oscilloscope is from VY, and the orange yellow trace is from VA. So what's happened is that we've driven we should be driving the conductance of both of these devices more positive. But what happens is that due to this, this RC effect, the voltage polarity inverts, right? So in this red area here. So the voltage across, say, the M2 memristor, it's going to be ground here, and its VY is this blue line. Okay, so it's positive. However, the voltage drop across the M1 memristor is going to be the difference between A and B. Now A has gone down to 0, but or the Y node here is still positive, and so you get a polarity inversion, and that's causing M1 to decrease its conductance, which, because it's a differential pair, has the effect of driving the synaptic state negative. Okay, so you run the classifier app and you see that most of your synapses are negative and they just won't budge. That's why. It's because of this problem. Okay, so there's two ways that we can get around this. We can do what we should do, which is to go into the Synapse app and manually initialize each one of those synapses. Make sure that you've driven the memristors into conductive states. Make sure that it's been initialized at least once. That'll sort of give the synapse a memory of those highly conductive states, and it will drive it towards that, and it will mitigate all this. The other thing that we can do, kind of the lazy man's way out here, is to just increase the pulse width. Okay, so if we just increase the pulse width, let's just move that all the way up here, just for the sake of demonstration. And let's go pick the 4 pattern again, and let's learn. What we can see is that it has no problem learning. Okay, so it's able to drive the state of the synapses, and rather than sort of keeping it in that negative territory, it's able to overcome the RC effects because our pulse width is now much bigger. Another thing that you can do is to pick the half sine wave. Now, instead of having sort of sharp transitions on your applied pulses, the half sine applies this sort of nice slowly varying signal, which helps you mitigate the RC effects. Okay, so the other thing that we can do, which is what we probably should do, is first to go to the Synapse app and sort of get a read on the state of our synapses. Which synapses work, which synapses don't work, and if they don't work, you might want to figure out why. It's going to be because there's a memristor fault of one form or another. Maybe you drove it too hard, maybe it's stuck high, maybe there's a wire bond issue. So, before we jump into the classifier app, make sure that you got some synapses and make sure that they work. So what we want to do is, in the Synapse app, first open up the console. Console is going to give us some indication of what's going on under the hood whenever we execute instructions, and it's going to be helpful in what we're about to do. Okay, so let's arrange everything so you can see both Memristor Discovery and the console. There we go. Let's click on Synapse 1 and hit Initialize. And it shows you all the instructions that are being executed, and down here it shows Synapse initialized successfully. Okay, so that's good. Synapse 1 is good. Let's go to Synapse 2, and it's taking a little while. It's usually an indication there's an issue. Okay, failed. State did not change upon application of anti-Hebbian cycles. In step 2, step 1, memristor could not reach target. Okay, so we have a potential issue with Synapse number 2. Let's move on to Synapse 3. That was successful. 4. Same problem as before, so Synapse 4. And 5 was good. 6 is good. 7 is good. And 8. Taking a little while, having issues. Okay. So we have discovered that there could be issues with synapses 2, 4, and 8. Now, knowing this, we can go back to the classifier app and we can run and see if we can notice if we have synapses that work, synapses that don't work, and if we can explain what's going on. Okay, so we have synapse 2, 4, and 8 are misbehaving. Let's just keep everything at the default settings. Let's learn on mistakes, and then let's do the ortho 8 pattern. Okay, what this does, if you recall, is each input is activating just one synapse. The pattern itself, let's check out the help menu here, scroll down. Okay, so the ortho 8 pattern, synapse 0, 1, 2, and 3 are all mapped to the true label, and synapse 4, 5, 6, and 7 are mapped to the false label. So when we learn this pattern, what we should hopefully see is synapse 1, 2, 3, and 4 should go positive, and synapses 5, 6, 7, and 8 should go negative. And if they don't do this, then we will not be able to learn with 100% classification accuracy. Okay, so everything is set. Let's click Learn. We're increasing the accuracy, sort of leveling off, looks to be about 65%. We're not able to learn everything perfectly, which makes sense because we noticed that synapses 2, 4, and 8 were not working. So synapses 1 here, that's positive, which it should be. This is synapse 8 is negative. Okay, remember synapse 8, this should actually be negative, but recall synapse 8 wasn't working for us. And the synapse 3 is positive, that's right. Synapse 4 should be positive, but it's negative, but recall synapse 4 wasn't working. And the rest should be negative. Okay, so this kind of makes sense, right? We can do the anti-ortho pattern and see if we can do any better. And the only reason why we would do better is because our synapses happen to be stuck in sort of the right configuration. Okay, so in this case, it's exactly the opposite. Synapses 5, 6, 7, and 8 should go positive. So we notice that synapses 8 here and 7, those are both positive. Synapse 5 is just positive, so that's working. Synapse 6 here is negative. And we noticed that synapse 6 was working, but it should be, see, this is the anti-ortho pattern, so that should be positive. So let's just try to learn, see if there's any way that this thing is gonna sort of get unstuck. It seems to be stuck negative. Now recall that there's two things that could be going on here. Either you don't have a high enough voltage in order to drive change, or maybe your pulse width is too short given RC effects. Now since we've initialized the synapses, I'm gonna guess by maybe increasing the voltage, we might be able to drive the change across some of these devices that aren't working, specifically synapse 6. Okay, so let's keep on bumping up that voltage and seeing if we can get it to go. Oh, we're starting to get synapse 6. Okay, so we increased the voltage, and that's what it took. Okay, so it was sort of stuck negative. Synapse 6 is climbing, and you know, as soon as this thing can get above 0, then you know, we're gonna get a little bump in our classification accuracy. You can see it's kind of going up. All right, it just passed 0, and we have our classification accuracy has gone to 1. Okay, so in this particular instance, we had some devices which were working, but it turns out they were kind of, the state was stuck in the state that happened to match our data set. You know, that's just luck. And then in the other case, synapse 2 required that we increase the voltage in order to get it unstuck. So this is all the stuff that happens in the real world, and anything that you design, any AHA computing circuit is going to have to deal with these kind of issues. Now recall that our adapter board has 6 sockets in there for 6 Memristor chips, which give us up to 3x redundancy. Okay, so we just showed you that you know, we had 2 chips in here, and 3 of the synapses weren't working. Now I would recommend that you go in and look at the individual memristors and see why they're not working and better understand that. But you know, we talked a little bit about hardware level redundancy. Okay, so what we're going to do is take some more chips and plug them into these sockets here, to the right and to the left of of the sockets in the middle, and add 2x redundancy and see if we can get this thing to behave a little better. See if we can actually get 8 good synapses by exploiting redundancy. So we're going to take out our adapter board here. Okay, so we have our 2 chips in there, and we're just going to add a couple more to the side, like so. You can see this is from the 16 wafer, and this is from the 28 wafer. Our packaging and logo is better as we go. Okay, so we're going to take this. We've added 2x redundancy, and we're going to add this back to the board. Okay, so in the Synapse app, we're going to now test to see if we've turned those previously misbehaving synapses into good synapses. So it was synapse 2, 4, and 8. Nice exponential sequence. So synapse 2, we're going to click initialize here, and look at that. Synapse 2 passed. Okay, 4. Let's initialize that, and that also passed. Okay, last but not least, synapse 8. Initialize that, and it also passed. Okay, so we took our initial 8 synapses formed of those 2 discrete MIM inline chips. We noticed that 3 out of the 8 synapses were not working. They were having a hard time being initialized into a higher conductive state. They were kind of stuck high. If you're having issues like this, I highly recommend looking at the individual memristors, maybe going to the board check experiment, looking at the hysteresis app, investigating the nature of these memristor faults and why the synapse doesn't work. That'll give you a much better understanding of what's going on and how things fail. This is the kind of stuff that you need to know if you want to design reliable circuits with real-world devices. Okay, so we have added 2x redundancy, and we now have a nice, fully functional set of 8 synapses. Okay, so now let's go back to the classifier app. Now that we know that we have some good set of 8 synapses, and see how this behaves. Okay, so let's just let's keep it on the default settings. Let's pick the ortho 8 pattern, which is what I was having trouble with before, and see if we can learn. Okay, so right off the bat, looks like it's working, except look down here, the synapse values didn't change. It was initialized into that state to begin with. So let's pick the anti-ortho 8 pattern and see if we can learn that. So the learning problem has exactly flipped, and every synapse that used to be positive should now be negative, and vice versa. Okay, so right away we see that most of the synapses have sort of made that state transition, but synapse 6 here is sort of stuck negative. It went up a little bit, but it really didn't get all the way up there. Now, this is one of the issues with the memristors, memristors in general, I think, but definitely these. They have different rates of adaptation, which leads synapses to have each synapse needs sort of a different level of energy to be imparted upon it in order to make a change. Now, it's also a function of the sort of initialized magnitude of the memristors. So a synapse could be negative, and the memristors could be conductive or not very conductive, and both of them could register, say, a negative value. And depending upon how they were initially set, it might take, say, a lot more time and energy to move one synapse from a negative state to a positive state than another synapse. So, more conductive might take a while to sort of undo that state change than another one. So we can keep on learning, see if that's going to have any effect. Notice that we have learn on mistakes enabled, so the synapses should only be getting updates if there's a mistake. And right now, the only mistake is really a function of this synapse 6. Okay, so we started with the default settings. We can just say increase the pulse width and sort of speed up learning. And we can see synapse 6 sort of taking well to increased pulse width and cross the 0 threshold, and we get perfect classification accuracy. Okay, so increasing the pulse width sort of made this thing behave better. Again, there's RC effects having to do with the board itself, and there's just the energy that it takes to move the synapse. Without going in and looking at all the devices specifically, it's hard to say which is the right answer there. So go back to the ortho 8 pattern. So let's see if it can unlearn. It's able to make that state transition actually much faster. So it's able to go from the ortho to the anti-ortho pattern. Synapse 6 was able to go from positive to negative actually very rapidly. So let's go back to the anti-ortho pattern, see if it can make that transition. Actually, it looks like it's working quite well now. So the likely cause of synapse 6 has to do with its initialization magnitude. Sometimes the more you work these things, the better that they get. Okay, so let's click clear plot here. So whenever we start again, it's going to start fresh. And let's see, let's pick, say, the 2-5 frustrated data set. Made pretty quick work of that. You can see some of the changes of the memristors, but really they were kind of initialized good to begin with. Now, if you want to scramble things up, you don't want to cheat, you can start random, hit scramble. And what that's going to do is apply anti-Hebbian learning. It picks a random subset of the synapses, and then it executes the FFRA instruction, which causes the synapses to get just all jiggered around and sort of randomly initialized. So it's like the scramble button, start it at a random state. So now that it's initialized random, let's learn. And let's see how well it does. Okay, so it got it almost immediately within the first epoch or so of training. Let's try the 2 pattern 2, 3, 4, 5 frustrated. Okay, so 4 of the synapses in each one of the patterns is active in both the true and the false labels, which means that they have no information content, and really the classifier has to learn to ignore them. So let's try to learn this. This is difficult. Notice here that synapses 4, right, and 3, and let's see, 5. So 4, 3, and 5. These are all frustrated. They're just being moved up and down, up and down, up and down, up and down. That's because in one update they're being pushed positive, in another update they're being pushed negative, and they're just getting tossed around. They're frustrated synapses. So what we can do, maybe lower the pulse width. That is essentially reducing the learning rate or the change in the memristors. If we click learn again, notice that our accuracy now goes to 1. The magnitude of those oscillations goes down because it's not being updated so much. It's not being railed one side and the other side and the other side. It's able to sort of hone in. You could continue to decrease the pulse width further and sort of hone in those values, sort of reach, try to bring them in towards 0, or at least calm those oscillations. Okay, so there's a lot more to explore. There's a lot more to classification with AHA nodes than meets the eye. But the more you get into this Memristor Discovery platform, the more you learn about differential pair synapses, the more you start learning about the ways memristors can fail, the better you'll be equipped to actually make circuits that function with real-world devices, and the closer we'll be to building a neural processor. Okay, with that, and until next time, have a good one.